everybody, let's do another example of an energy interaction diagram with a slightly more complicated setup. Suppose we have this toy car and this spring. The spring will be compressed a certain amount and then let go. The car will be sped up on this track. It then reaches this ramp, which points straight up. Let's ask two questions. First, what is the speed of the car when it is released by the spring? And second, what is the maximum height that the car reaches when it travels up off the ramp? We can use energy interaction diagrams to describe both of these. However, there is an important distinction that we have to make. That distinction is the interval over which we're thinking about the energy interaction diagram. Energy interaction diagrams always involve a change between 2 points in time. For example, our initial state could be when the spring is compressed all the way, and our final state could be when the car reaches its maximum height. However, that would not be able to tell us anything about how fast the car was moving when it leaves the spring. In order to do that, we would have to pick a different final state, namely the moment that the car leaves the spring. Picking the correct interval is important because if you pick the wrong interval, you won't be able to get the values that you're interested in. Let's start with the first question. That is, how fast the car is moving when it leaves the spring. Let's assume that the spring constant is 50 newtons per meter, the mass of the car is 1 kilogram, and that the maximum compression of the spring is 1 meter. Let's see if we can draw an energy interaction diagram for this case. See if you can figure out which energy systems are changing that we need to care about. I come up with two energy systems. The first is the potential energy of the spring itself. Because the spring is being compressed and then allowed to relax, that potential energy is changing. The second energy system in this case is the kinetic energy of the car. The car initially starts with 0 speed when the spring is maximally compressed. When we let it go, the spring then pushes on the car, accelerating it and giving it kinetic energy. Let's write out the energy interaction diagram for this case and see what we get. Notice I'm explicitly stating what our interval is. Our initial state is when the spring is compressed, and our final state is when the spring has been relaxed and the car has just separated from it. Now let's draw in our energy systems. Here's our potential energy bubble for the spring. We know that the potential energy in the spring is decreasing because it is expanding. It was originally compressed to 1 meter shorter than its equilibrium length. It then expands until it is back at its equilibrium length, so its potential energy is decreasing. Notice I've included the indicator here. Delta x is just the difference between the length of the spring and its usual equilibrium length. The initial value for x is 1 meter, and the final value for x is 0 meters. Now let's do this for the car. We know the kinetic energy of the car is increasing because we stated that it started from rest. Our initial state is when the spring is compressed by 1 meter and the car is at rest against it. Our final state is when the spring has re-expanded to its equilibrium length and this car is now traveling this way across the track. The car's initial velocity is 0, but its final velocity is unknown. That's what we're going to try to solve for. Now, is this an open or a closed system? In general, systems like this would suffer from friction, which would be removing energy from the system as the car traveled. However, for the purposes of this example, we're not going to include friction and just pretend that no energy is lost at any point. This means that the system is closed. So what is our statement of energy conservation? If we're able to draw an energy interaction diagram, we should always be able to write down a statement of conservation of energy. All we do is add up the changes in the individual energy systems and set them equal to the energy entering or leaving the system in the form of heat or work. There's no heat or work associated with this problem, so the statement of energy conservation just looks like this. The change in the potential energy of the spring plus the change in the kinetic energy of the car equals 0. Let's see if we can write this out and solve for the final speed of the car. The potential energy of a spring is just 1/2 times the spring constant, k, times the distance the spring is from its equilibrium length. Since the spring constant is not changing, we can write the change in potential energy like this. The change in the potential energy of the spring is just 1/2 times the spring constant times the change in the value of the distance squared. Next, let's do the same thing for the kinetic energy. Let's now expand these delta terms in order to actually figure out what the values are. All we've done here is use the definition of change to expand this equation out. We know most of the numbers in this equation. We know k, it's given. We know the final position of the spring, the initial position of the spring, the mass of the car, and the initial speed of the car. So let's just plug in those numbers and see what we get. Here we go. This is a complete equation that explains how the energy moves from the potential energy of the spring into the kinetic energy of the car. All we have to do now is solve this equation for the final velocity squared, and we're done. And there's our answer. The final speed of the car, after it's released by the spring, is the square root of 50 meters per second. Now we're interested in figuring out how high the car goes when it leaves the ramp. Something interesting to notice, the interval that we just analyzed is included in our new interval. Since we know the speed of the car when it leaves the spring, we could call that moment the beginning of our interval. But there's no reason that we have to do that. We could also pick the same initial state that we did for the first case. As long as we're able to write down an equation with only one unknown, it doesn't matter. Let's reanalyze this system, but this time we'll take the final state to be when the car is at its maximum height. Notice one thing that's nice about picking our interval this way. Because we're taking the initial starting point to be the same as we did in the first case, we've already taken care of one of our energy systems. The fact that we're looking at our system for a longer period of time doesn't change the way the spring behaves. It's still going to start compressed and then relax until it reaches its equilibrium length. What about the kinetic energy of the car? Do we need to include that here? The answer is actually no. When we're doing the energy interaction model, the only energy systems we have to include are energy systems that are different at our initial and our final points. We already know what the speed of our car is at the initial moment that we're looking at our system. It's 0. We're taking our starting state to be when the spring is maximally compressed and the car is at rest. So the speed in that moment is 0. What about the final speed? Well, we're taking our final state to be when the car has reached its maximum height. If we think about this carefully, we realize that the car is not moving when it reaches its maximum height. It first travels up and then travels down. Its maximum height is going to be right in between the upward travel and the downward travel. In other words, when the car has momentarily frozen in the air. So by picking our initial and final states carefully, we've allowed ourselves to completely ignore an energy system, in this case, kinetic energy. So what is the other energy system we need to be considering? Well, the answer is, of course, gravitational potential energy. The car starts on the ground, but it's then flying into the air, meaning its gravitational potential energy is increasing. Let's write that in our energy interaction diagram. Because the car is traveling upwards, its gravitational potential energy is increasing. The initial height of the car is 0, it's on the ground, and the final height of the car is unknown. It's what we're trying to find. However, as before, we only have one unknown in this problem. We don't know the final height of the car. We also need to change our statement of energy conservation. We no longer have kinetic energy in this problem. Instead of spring potential energy and kinetic energy, we now have spring potential energy and gravitational potential energy that are changing. Now, just as before, we can write out these equations in more detail. Now let's plug in values and see if we can determine the final height. Just as before, we only have one unknown. In this case, the final height of the car. Let's solve this equation for the final height and see what we get. And there's our answer. The maximum height that the car reaches is 2.5 meters. There are a couple main ideas to take away from this example. First and foremost is the importance of the interval when you're doing these problems. By being clever about the way you pick your interval, you can often remove work from the problem you would otherwise have to do. It is true to say that the kinetic energy of the car is changing during this process. However, it's only the initial and final states that matter when we're doing energy interaction diagrams, so we don't need to include the kinetic energy because it's the same at the initial state and the final state. The other thing we want you to take away is that it's very simple to write down a conservation of energy equation if you're able to draw an energy interaction diagram. Once you have the correct energy interaction diagram, you just have one term in the equation for each of the bubbles, and then a term on the right-hand side for any energy entering or leaving the system. In this case, that was 0. This recipe will work no matter how many energy systems you have in your problem. If you want to solve for anything interesting, you're going to have to set up your problem in such a way that there's only one unknown. But you should always be able to do this.